Hi, it's oscilloscope review time. What I have here on the bench today is a Hantek DSO2D10 dual channel 100 MHz bandwidth 1 gigasamples per second digital storage oscilloscope. It is a relatively new entry-level oscilloscope released by Hantek within this past year. I requested this unit for a review from Banggood, as what caught my eyes is that beyond the standard 2 oscilloscope channels, this scope also has a lot of bells and whistles. For instance, it has protocol decoding capability, and also the D-series has an arbitrary waveform generator output channel. Better yet, all these features come in at just above $200, which is very affordable. So on paper, it is an excellent entry-level scope, and of course, we will test out some of the key features in this video and see how well it lives up to the expectations. I will also provide a product link in the video description below, and if you're interested, you can hop over to Banggood's website and check it out. In this DSO2000 series, we have the C model and the D model. And keep in mind that only the D model comes with the signal generator here. And you can see we have some very impressive technical specifications here. Just wanted to flip through and show you a few. For example, the acquisition rate is at 2000 waveforms per second per channel, and memory depth is at a maximum of 8 megasamples per channel. So that's very, very impressive. If you look at the triggering capabilities, we can see that we are quite capable here, as we have many options to do the triggering. So I will go through these capabilities a little bit later. If I were buying one for myself, choosing the D model, which comes with the arbitrary waveform generator, seems to be a no-brainer, as the D model is just ever so slightly more expensive than the corresponding C model. Also forgot to mention, within each model, we also have the 100 MHz version and the 150 MHz version. Again, in my opinion, you will see later in this review that the sweet spot is the 100 MHz version. But if you really need the extra bandwidth, of course, you can certainly spend a bit more on the 150 MHz version. Out of the box, you get all your standard DSO accessories as expected. What is interesting though is that you only get a single set of the probes instead of a two for a dual channel oscilloscope. But the standard P150 probes are pretty cheap. You can always get an extra set afterwards. Now, curiously enough though, you do get two sets of these BNC to alligator clips, although we only have a single AWG output channel. The power cable came in also is not your standard North America cable and does not have the ground prong here, but you do get an adapter if you need to use it. Now I have plenty of power cords lying around, so I would just use my own. You also get a USB cable, as this scope does come with its companion PC software, which we will take a look later on. Okay, let's power it up and take a closer look. Now, modern scopes do take a bit of time to boot up, as the software base is typically on top of some kind of operating systems. Nowadays, though, a lot of embedded systems being used that I have seen are based on some kind of Linux kernels, as Linux is open source and does not have the licensing premium associated with commercial products such as Windows Embedded or Windows IoT. The boot up time for this scope is actually quite respectable. I measured it was roughly around 10 seconds, which is not bad at all. Now, the first thing you will notice is just how quiet this scope is. Now, I do not hear the sound of a fan. Not sure whether there is a temperature controlled fan or it simply just did away without a fan. I guess we'll have to take a closer look later on when we open it up. The controls on this scope are very well laid out. You don't really need to refer to the manual to get started really quickly, and they're very logical. If you have used any kind of digital oscilloscope before, you'll have no problem using this scope. And one thing I like about this scope from the get-go is it has a default setup button, and this is actually very useful if you mess up your settings or you don't remember what the settings you were and you want to just restore to the default. You can just press this button and it will restore to the factory default settings. By default, both of the channels are enabled. Now, I played around a little bit earlier. I did notice that the default setting is not exactly what I expected. For example, the probe is set at ×1. In general, you are using a ×10 probe, so I would just correct that. And so later on, we don't have any surprises. And by default, whenever you press a button, there is a loud beep. Now, that can get pretty annoying very quickly. Of course, you can always turn it off in the setup. But for this video, I'm going to just leave it on, as you can hear when I'm pressing buttons. At least you know something is happening here. Now let me hook up the test signal here and we'll take a look. Let me just use the auto set to automatically acquire the signal. And you can see that we acquired the signal with no problem at all. And earlier I did adjust the compensation here, so now you can see the square wave looks nice and clean. Of course, you can always manually make an adjustment here, and you will see that it's not particularly fast. I wouldn't use speedy to describe the control, but nevertheless, it is manageable here. Now, interestingly, I'm not sure if you saw that, as soon as I switched the vertical settings here, the trigger level dropped all the way to the bottom. So I have to readjust that trigger level to get the waveform re-triggered to a stable waveform. Let me manually adjust the time base a little bit, and as we reduce the time base, or rather increase the time base, you can see that it is actually getting more and more sluggish, but it is to be expected for an oscilloscope in this price range here. There's nothing to complain about as long as everything works here. Let's take a look at the system information to see if we can figure out anything here. So the system info, and we have our model number, serial number here, and let's see what is on the next page. There's some legal information, so let's take a look, and I think I can use this button to get to the legal information. As we suspected earlier, you can see that the libraries used here are Linux static libraries, so this unit is based on Linux. And one thing funny is that if you look at some of the font used here, they are not the standard size. And if you see that G, it is all the way up. So I'm not sure if this is specific to the design or there's some kind of limitations there. Not entirely sure. Now, almost everyone watching this channel probably already knows the basics of using an oscilloscope, so I will not go into a lot of details here, but just want to highlight a few things that I consider are some of the unique features of this scope, and maybe I'll do some quantitative analysis to see how well the measurements matches those in the spec. One of the key selling points of this scope is, of course, the included arbitrary waveform generator. You can see that the output from the signal generator is actually multiplexed with the external trigger BNC, so there's no additional connector on this scope. They are using the same one here. Now let me plug in the generator here. I'm not sure if you see this. As soon as I plug it in, let's watch this baseline here very closely. When I plug it in, you will see that it dropped by a little bit. Now the waveform generator currently is off, so there's some DC offset that you can't get rid of. So now let me enable the waveform generator here. And we're looking at a sinusoidal at 1 kHz. So let again automatically reset it to acquire that signal. No problem at all. So let's see the waveform generator. We can change the waveform to square, ramp, exponential, noise. So these are the built-in waveforms, of course, but we don't have any arbitrary waveform built in yet. So we'll have to take a look at the included software. And let's see what is on the next page here. We also have the modulation capability, so let's take a look. And right now the modulation is off. Let's sure we do amplitude modulation here. Let's turn it on. And as you can see, we're doing some AM modulation here. We can zoom out a little bit. And of course, it's not very stable here. And that's typical on this kind of modulated waveform. And let's maybe change our carrier frequency to be a little bit higher. How do we do this? It seems that the only way we can change the frequency is using this knob here. Now, That's going to be quite tedious if you're changing, let's say, all the way up to 1 megahertz. And I'm not sure if there's a way we can use a keyboard to enter. Now, of course, we're seeing some aliasing here. So for that, we can, we change it back. Let's change it again to, let's say, 10 kilohertz. And the modulated signal looks relatively clean here. Let's again change it to the next page. And let's see if we can have another modulation. We can also do frequency modulation. The amplitude. There's a little bit of delay, and this button is very touchy. As you can see, when you scroll it through, it just scrolls back and forth. And let's do frequency modulation. So unfortunately, right now time base is too slow here. Yep, you can indeed see that the signal is being modulated by the frequency here. Let's see what else we got here. Let's take a look at the modulation menu again. Return. And by the look of it, we can also change the duty cycle, but not during the modulation here. So let's turn the modulation off. And let's see if we can change the duty cycle. Nope, we can't change the duty cycle for this waveform. So let's take a look to see if we can do that for a square wave here. So now it's at 10 kilohertz. Let's change the duty cycle. Yep, now we can change the duty cycle. As you can see, that's actually quite nice. You can use this to generate different shapes of pulses here. Now, as you can see, the supplied waveforms are actually quite limited. We only have this few waveforms that are included. But the good news is you can always use the supplied PC software to build more arbitrary waveforms. So let's take a look at how that is done. There is very rudimentary arbitrary waveform editor software included, and you can either use the included additional waveforms here as is, or use them as base to build your own. Now, I have to admit, the editing capability is quite limited, and there's no way for you to be able to create an arbitrary waveform precisely in the UI. But luckily, you can easily create the desired waveform by supplying all the 4096 data points between -1 and 1 and save into a CSV file. The program can then read in the CSV file as is, and it can even convert it to the proprietary ARB format. When the oscilloscope is connected to the PC, you can use the wave editor software to upload the designed waveform directly up to the scope. Now, one surprise is that the transfer waveform does not persist on the oscilloscope and will be cleared when you power cycle your scope. This is rather unfortunate, as I'm sure that it's very easy to store these arbitrary waveform files onto the scope itself, but for whatever reason, it was not implemented that way. But the waveforms can be stored onto a flash drive and loaded via USB. So let me show you that. And earlier, I just saved the staircase signal that I generated using that wave editor and exported as an R file onto this flash drive. So let me plug it in. And you can see that it recognized the flash drive. So let's go back to the waveform generator here. And we press this recall button. You will see that right now we can actually load the file from the disk here. Now, if you look at the folder structure here, it's a mount U disk, so that clearly indicates it's a Linux operating system underneath. Interestingly though, you can actually go to different directories and we can see all the files, the structures on this system here. So that's a little bit interesting. In my opinion, they should have just limited to which directory you can browse to. But anyway, let's go back to the disk. This is our mounted flash drive, and I have this staircase. Whoops, it's a little bit touchy here, and the timing is not implemented perfectly here. So now let me just load that staircase signal. Now, as you can see, we have this staircase signal loaded, and we can zoom in and adjust, and you get an idea here. Again, the trigger, for whatever reason, by default is very close to the bottom of the waveform, so you have to adjust it manually to make sure that the signal is triggered and is stable here. So let's adjust here. Hantek uses Keysight's I/O library, which I think this is a smart thing, as you can use SCPI or SCPI, standard commands for programmable instruments, to control the oscilloscope from your PC. And this is almost a necessity if you intend to use the scope to do any kind of automated testing. So right now we can see the bandwidth of the channel, and you can see when we send that command, it returns 0, means it's not limited. And we can check our trigger setting as well. So let's issue the trigger mode. And we'll see that right now is set as triggering by the edge of the waveform. Now we can of course set it to something else. Let's say set it to SPI, and we can then read it back. You will see that the mode, it is SPI here. And of course we can set it back to edge. Now, just to test another thing, we can try to see what the memory depth is on this acquisition here. So let's send that command over, and we'll see that by default, the acquisition depth is at 4K. So as you can see, it is very, very useful. On the computer, you can pretty much control everything on the scope via software here. For example, you can adjust the center here, as you can see on the screen here. And of course, you can adjust your vertical settings, and pretty much everything you can find on the scope, you can control it here. Of course, you can also enable your arbitrary waveform generator here as well. So it definitely has a cool factor to it, but I don't find it that useful. Next, let's take a brief look at the memory depth of this oscilloscope. Memory depth is important for a DSO, as one of the reasons you want to use a DSO is for its single-shot capture capability. And the larger the memory depth, the more details you can capture at one time. With 8 megasamples, you can capture a lot of information. So let me give it a quick demonstration here. Right now I hooked up a power supply to the input of the oscilloscope, and I wanted to measure the power on characteristics. So before we start, let's take a look at our setting here. By default, it is configured at 4 kilopoints per second. That's the default setting. And let's use the default as right now. Let's take a look at the triggering menu here. Right now we're set to be edge triggered and on the rising edge. So that is good enough. Let's take a look at the single capture, and it's very convenient here. You can see that we have the single sequence here, so I press that, and we should be able to do the single trigger. And of course, I have already set up my trigger to just above the 0 DC line here. Let me turn on the output from the power supply here. And now you can see we captured the waveform. Now, this waveform only has 4,000 points here. So if I zoom it out, by expand the time base, you will see that it doesn't have enough points at the lower end here, so you can't see the details. Now let's do the same capture again, except this time we're going to be using the memory depth of 8 megasamples here. So let's change it to 8, and let's do single capture here. Enable the output, and boom, we have the waveform again. So now let's zoom it out. You can see that we have a lot more details on the lower end here. With the 8 megapoints memory depth, even at 200 microseconds per division, we still have enough details to be observed here. And I want to use another example to demonstrate the importance of the memory depth. Let's say I wanted to capture some signal at 20 milliseconds per division, and once I capture it, I wanted to expand my time base and take a look at the details. The reason I wanted to do that is so that I have enough samples to be able to see what the signal looks like. And right now you can see that because the memory depth is at 4,000 points, we don't have enough details to show each of the waveforms. So that's where the high memory depth comes into play. So now let's set it back to 20 milliseconds per division, and let's keep it running. But this time I'm going to change the acquisition memory depth from 4K to 8 meg. So again, I'm going to do the same thing by stopping my sampling here. And now if I expand my horizontal division here to 20 microseconds per division, you will see that we can clearly see our signal train here. So of course, now you can zoom in forever. You can examine all the signal details as you would like to. Now this brings us to the next topic, which is the protocol decoding capability of this oscilloscope. In the past, you only see protocol decoding capability included in higher-end oscilloscopes. Now I'm very excited to see that capability is actually included in a budget scope like this one. Now let me give you a quick demonstration here. For that, I'm going to start running again, and let me turn on the decoding capability. And not sure if you noticed, as soon as I started decoding, you see that the memory depth dropped to 4 kilopoints. Unfortunately, this is a limitation of the scope. For example, if now I press acquire, you will see that I actually don't have the ability to change the memory depth any higher. Now this is a limitation, unfortunately, but nevertheless, you do have the ability to start decoding now. In order to successfully decode a UART signal, you do need to know at which baud rate you are running the signal at. So for that, we're going to change the baud rate, and we know that we are running this at 11.5200. Let's do that. And by the way, also you need to make sure that the trigger level is above the signal, otherwise you will not be able to decode it as well. So that's just something I found out through trial and error. So now if I do this, and we can see that we started seeing the signal coming through. These are the decoded signals. And if I stop the frame here, you will see that these are the signals being decoded right at the bottom in the hex form. And there's some more limitations besides the aforementioned memory depth when decoding a signal. When you are running the signal, if I change my time base, you will see that we are not able to see actually what is being decoded. Unfortunately, that has to be at a certain time base before you can see it. But if we stop it, for example, we expand the time base again, we can see the signal reappearing again. So that's just something you need to remember. Now, of course, you can always see this, instead of listing right here, you can also, let's try to decode it another way. We can change it to display as a monitor here. And when we enable that, and let's why it's not showing here. When we enable that, yep, we should see that the data comes up in this tabular form. So that's another way for you to capture the decoded data. And of course, besides being able to decode UART signal, let me change it back here. And as you can see here, we can also decode CAN, SCPI, and I2C as well. So that's quite impressive. This scope also has very comprehensive triggering capabilities that I only scratched the surface. If I take a look at the trigger menu, you will see that we have all sorts of different triggering capabilities. You have your standard edge triggering, you have your slope triggering, and pretty much anything you can think of, you can find it here. You can trigger by the specific protocol, or you can trigger by a specific pattern. You can even do conditional triggering. You can find all the details in the user manual. Now let's take a look at the actual bandwidth of this oscilloscope. For that, I'm putting in a signal from the HP8642B signal generator. The signal currently is at 9 dBm, is at 100 MHz. One thing I forgot to mention earlier is that the input impedance to these both channels are at 1 megaohms each, and there's no option for the 50 ohm termination here. You also notice that the signal is a little bit wobbly here, and that is actually the artifacts introduced by the oscilloscope, not from the signal generator itself. So let me turn on some measurement. As you can see, we are indeed able to measure the signal at 100 megahertz. And now let me start to increase the input frequency and get an idea of what the amplitude looks like on the oscilloscope itself. So let me just increase. Right now I'm at 110 megahertz. Of course, there are some variations due to the imperfect matching of this cable here. But let's increase a little bit more. Let's increase it all the way to 150 megahertz here. So now I'm at 150 megahertz. Let's do another measurement here. As you can see, we're indeed at 150 megahertz and no problem at all. And as you can see, even at 150 megahertz, this 100 megahertz scope can handle just as well without any apparent attenuation here. Now let me keep increasing the input frequency. Let's do 200. Now the input signal is at 200 megahertz. And if we press the measurement manual, you can see that indeed we're reading 200 megahertz. At this input frequency, you can see that the amplitude is significantly attenuated. Now it's at about 50% of what we had before, so that clearly already dropped off that 3 dB bandwidth. But as you can see, the scope itself remains usable. So the limitation really right now is just the front end. If the front end has a little bit higher bandwidth, I suspect you can actually even push it further. As let's just increase the frequency a little more just for fun. Right, so for instance, right now we're at 250 megahertz. You can still see the waveform itself. And if we just use the measurement key to see that we're at 250 megahertz, so indeed, the digital portion of the scope can handle well over 250 megahertz. Unfortunately, the front end is limited to that 150 megahertz also bandwidth. Next, I wanted to measure the rise time of the scope. For that, I'm hooking up a avalanche pulse generator that I built a while ago that is capable of generating very fast rise pulses. And for the 100 megahertz version of the scope, the rise time is specified as less than 3.5 nanoseconds. So let's give it a test and see whether or not that is accurate. So let me power on. And let's just do a auto acquire here. Let me expand the time base. And I think I might need to adjust the signal down a little bit. The pulse is very high, unfortunately. By the way, it's not 100 volts. This is just because right now the channel 1 is set at times 10, whereas the input in reality is just time 1. Anyway, so that's just something to remember there. And so right now, let's just stop this frame here. You can see we started roughly at the beginning of that center line here. And we went over this just a little bit. Actually, it's less than 3 nanoseconds. As right now, you can see the horizontal is at 2 nanoseconds per division. So this is 2 nanoseconds, and this is 4 nanoseconds. So it's definitely within 3 nanoseconds from this measurement here. As a 2-channel scope, it also supports XY display mode. As you can see here, I'm currently outputting two 100 Hz signal. These are 90 degrees apart. So I should be getting a circle on the display. But instead, you can kind of see the shape there. Given the resolution, the result is really not that great, and it's not all that useful. This is a little bit disappointing, as my 10-plus-year-old Rigol 1052E can do a slightly better job. In fact, the handheld 2D72 from Hantek I reviewed not too long ago did much better than this benchtop oscilloscope. This scope can also be used as a digital voltmeter. To do that, we can press measure and we go to DVM and we can enable that measurement here. So as you can see now, we have the measurement showing on the screen. But in my opinion, that is just a gimmick, as all oscilloscopes can measure the input voltages. And here you just get a dedicated display for the DVM functionality. Keep in mind that the ADC for oscilloscope is typically 8-bit. That limits your voltage reading resolution. But nevertheless, we can give it a try. Here I have a battery, and we can use that to measure the voltage here. Let's take a quick look. And no problem. As you can see that, we can measure the voltage without any issue. Of course, as I mentioned earlier, you do have some limitations. And also, as you can see, even without any measuring, you can see that the voltage is not at 0. This is actually very typical for oscilloscopes to have a relatively high offset voltage. Opening up the unit is quite straightforward. There are only 4 screws on the back cover here. And once you remove that cover, there is an additional shielding cover on the main board itself that can be removed via a few more screws. Once that is removed, everything is in clear view here. Now, one thing to point out is if you look at this side, there is a mounting space for a fan, but clearly there's no fan included on this unit. So I guess the designer must have concluded that given the thermal requirement of this unit, fan is not needed. I don't think I'm going to take it down any further, as the front panel probably just the front panel circuitry. There's nothing important to see there. And the main board really is this board at the bottom here, which you can already pretty much see everything. So I will zoom it in, at least try to zoom it in and take a closer look. But that is pretty much all there is to it. And I did remove the shielding covers from both of the channels, as you can see here. I'm going to zoom it in a little bit so you can see it more clearly. And by the look of it, the original design also supports solder-in shielding cover, as you can see these slots here. But luckily, we don't have these soldered in. These shielding covers are screwed in by 1 screw on top of each of the sections here. And from the view here, you can see that both channels are pretty much identical. They have this one solid-state relay, which is a LT210, and along with a mechanical relay to switch different attenuations from the input. And here we have this 74HC4501D, which is an 8-channel MUX, 1 on each of the input channel here. And then we have this LMH6702, which is a high-speed op-amp from Texas Instruments that supports up to 1.7 GHz bandwidth. And let me zoom it out a little bit. You can see a little bit more here. And also there are a few SMD chips sprinkled here and there, these 8-pin chips. I'm not entirely sure what these are, but probably they're some kind of op-amps by the look of it. Not entirely sure. And if you look at the marking on this board, it says it's version 1.7 and was manufactured 2021, January 14th. That is actually very recent. And unfortunately, the 2 main chips here, I can't find any information on. First of all, this one chip, all the markings are sanded off. Obviously, they were trying to hide trade secret here, but presumably this is one of the FPGAs or ASIC that is used in this oscilloscope. And the other one, this is a Lemon Tree branded IC. Now, I cannot find any information on that one either. The chip hiding back here is a DSO2D10, which is a 12-bit 165 megasamples per second digital to analog converter chip. And I'm pretty certain that that is the DAC driving the arbitrary waveform generator's output. Now, curiously enough though, if you take a look at a board layout, towards the waveform generator output BNC, there's really nothing here. And there's nothing underneath this board either. As you can see at the bottom, it's very clean. So the only thing I can assume is somehow the signal is routed to the output via the inner layer. Now, given the relative location of this 8-pin chip to this DSO2D10, I assume that this is the output op-amp that drives the output from the waveform generator. If you look at the other side here, you will see that we have a memory chip here, and on top of it, that's the F1C200S, which is a ARM CPU. So that CPU presumably is used to do a lot of the heavy lifting of the operating systems and controlling the user interface and so on and so forth. I assume at one point this oscilloscope was designed with serial port in mind, as you can see this empty footprint right here. And also there is an unpopulated IC by the look of it that could be your serial port transceiver here. Now I assume that the USB functionality is handled by that F1C200S ARM CPU directly. And on this end you can also see some DC-DC converters that is implemented here. Those are used to supply the voltages required by these ICs here. Towards the other side, you will see that we have a few linear regulators and we have some test points. Here I'm reading a plus 5 volts and here's a plus 8 volts and there's a minus 8 volts by the look of it right here. So presumably the plus and minus 8 volts are used for op-amps and the 5 volts are used for your logic chips. And here's a look of the power supply module. You can see that we have 3 voltages provided, plus 5 volts, plus 8 volts, and minus 8 volts. Now this does mean that it will be a little bit tricky if you do want to convert this scope into a battery-powered one. All in all though, I'm quite impressed with this Hantek DSO2D10 oscilloscope, especially considering the features it offers, such as the built-in signal generator and the protocol decoding capability, although somewhat limited. I don't think you can find many alternatives at this price point with the performance and capability you find in this DSO2D10. And that pretty much concludes this review. If you have any questions or wanted to check on something specific about this DSO, please leave me a note in the comment section below. I hope you enjoyed the video and please remember to give it a big thumbs up and remember to subscribe. Your continued support is greatly appreciated. I will catch up with you next time.